So in this video, we're going to learn about vectors. Now, vectors are really at the heart of a lot of the mathematics that are used in all of UP1 and UP2. So having a really solid understanding of them is very important. I'm going to go through the basics in this video, and then there's also the supplemental reading from the textbook and an additional optional video that you can watch if you find that you're struggling with any of the problems or ideas. All right, so what we mean by a vector is that it's something that has not just a size, but also a direction. So things are either scalars or vectors. So we have something called scalars, which is something that has no direction associated with it. It is just magnitude, essentially. So something like mass. So examples of this would be, say, mass. Speed, I can say that I'm driving, 10 miles per hour slowly down the road, but I don't say the direction of it. So then it would just be the speed. So those are common examples. On the other hand, we can have something which we call a vector. And so vectors have a magnitude, meaning a size, and very importantly, a direction associated with them. So examples of vectors are going to be things like position. So where you are in a coordinate system is relative to some axis. So it's a position vector. Or we can talk about velocity. So velocity would be not just a speed, but a direction. So velocity would be, say, 10 miles per hour east. Now all of a sudden my speed became vector velocity. And then we also have common ones we'll see in this course. We have force vectors, but then we have other things like electric field vectors, etc. In this course, we'll also deal with acceleration vectors, etc. So quite a few things that we'll see are vectors in this course, and I'll define when we make a new quantity, whether it's a vector or a scalar. So the notation for vectors is that we denote it by, say, some vector A, and we'll draw an arrow over it to show that it's a vector. And so then the magnitude of the vector would be denoted by drawing these straight lines commonly used for absolute value around the vector. We don't call this, it's not just taking the absolute value though, as we'll find. Instead, that's just our new notation for how we express a magnitude of a vector, or we can just draw the vector without the arrow over it, and then that would denote it also as a magnitude. So that's going to be our general notation that we use. So now we want to go ahead and talk specifically about how we can write out vectors in different ways. We can either write out, their x and their y components, x, y, and z if it's in 3 dimensions, or we can talk about them, say, in like polar coordinates with like a angle and a magnitude. So here I'm going to then just talk first about unit vector, what we'll call unit vector notation. So unit vector notation is a commonly used notation for vectors in physics. Now, before I get into writing it all out in this like sort of messy math way, I want us to just take a step back and say every vector we're going to encounter, whether or not it's force or acceleration or position or velocity, they can all be visualized by imagining like a treasure map. Which is that you could imagine somebody says, oh, you have to walk to the palm tree and then take 5 strides towards the sun, and then you have to take 10 strides towards the ocean or whatever, and then dig a hole and find your treasure. All of those, right, are essentially vectors. And then when the way that they add and combine is the same way in position vectors like a treasure map as it is for electric fields or forces. So now let's go ahead and see how we can write this out mathematically. So unit vector notation for a typical vector, let me just draw one in the first quadrant. So let me start with a vector here, and I'm going to draw my vector A in the first quadrant. And it is then going to have, in this case, being drawn at some angle, you know, say here, theta, with my positive x-axis. And it has some length here, which we would call the magnitude of vector A. That's the length of the vector itself. But what we can also notice is that this vector I could get from my start to my end point by walking along x and then walking along y. So every vector can be written in its x and y components. Meaning that instead of just saying, okay, you're going to walk some distance at some angle, you could instead walk along x and then walk along y. So we have notations here for this. One is just called our component notation, which is one you're used to for position, but it also works for other vectors, for force, etc. And the component notation is that vector A can just be expressed as its x component, comma, y component with parentheses around it. And this works, but we don't use it as commonly in physics, and more often we use what's called unit vectors. So unit vector notation is that I would then take my vector A, and then I'm going to write it out and then explain each part. I'm going to have my x component, the amount that I walk along x, and then I'm going to write I hat. That's a unit vector. I'll talk about that in a second. And then, because I'm also walking in the positive direction here for AY, I'll say plus AY and then J hat. And that's going to be a unit vector that indicates that I'm walking along my Y direction. So these here, AX and AY are the components of my vector, right? So AX and AY are just the components of my vector. And then I have these unit vectors, I hat and J hat. So I hat and J hat, and then for 3 dimensions, we have K hat, are unit vectors. What that means is that they are vectors with a magnitude of 1. So that the magnitude of I hat equals 1. That would be another way to write that. So what that means then is the only purpose of the unit vectors is to denote a direction. So the only purpose is to denote a direction. And the convention is IJK, which are just alphabetical. So IJK is the same as X, Y, Z. So I hat is used for the X component, J hat is used for the Y component, and K hat is used for the Z component. Some people prefer to just use X, Y, and Z, and you're allowed to do that, but you do have to be able to interpret problems or questions that are given to you in the IJK notation. So in this case, then, we can look at our vectors, and we can see that we can write it out as the X component. Here, I'm looking at the X component times the unit vector I hat, and then plus the Y component times the unit vector J hat. And that would then be our unit vector notation. Okay, so the other notation that we have would be our magnitude and angle notation. This is sometimes also in 2 dimensions, can be thought of as just our polar coordinates in some ways. It'd be your distance along R and then your angle. But it's not always a coordinate because sometimes it's an acceleration vector or a force vector. But again, all of these same things apply. So the magnitude and the angle notation is basically that we would have the magnitude of the vector A. And what's important is to remember that this is just the length of the hypotenuse of this right triangle, where we would have to redraw what I had above, the vector A, and then I had my component, AX, and my other component, AY. And so that A, magnitude of A, is always the hypotenuse of the right triangle. And so the length of that hypotenuse, therefore the magnitude, can be written as just the square root of the squares of the sides. So just our good old Pythagorean theorem. So AX squared plus AY squared equals the hypotenuse squared. And so we end up then with our very key result, which we will use throughout this course for the magnitude of a vector. And then for the angle, we want to use trigonometry. You just want to use the triangle. So you always want to draw the triangle and you want to use your trigonometry. And so in this case, what we might see here, and very often we just stick with the tangent of theta. So the tangent of theta in this case would be equal to AY over AX. Now one thing, oops, I erased versus, I did that again. I will get used to that. And so I'm going to just rewrite this. The tangent of theta, again, is opposite over adjacent, AY over AX. So SOHCAHTOA, if that's how you learn sine, cosine, and tangent, that's going to come back full force. And so this then will allow us to calculate theta if we know our components. One thing I'm going to say is to be careful of the quadrants for theta. And that's going to be because when you're working out the angle, then what we have is that, let's say I have theta over in my first quadrant. Well, this has some positive x component and positive y component. But over here, I'd have a negative x component and a negative y component. And so this vector in the reflected, basically vector in the fourth quadrant, these are going to have the same tangent of theta. So it depends on your calculator. Some calculators will give you both, but most calculators will give you the one that's in the first quadrant. So if you know your answer is supposed to be in the third quadrant, then you're going to have to adjust it. So adjust your angle according to the quadrant you're in. So to summarize what we've done so far, basically we have talked about just what a vector is. It has a direction. And then also we've learned to write it in unit vector notation so that we can write it as a x component I hat plus a y component j hat, and then plus a z component k hat when we get to 3 dimensions. We've learned how to write the magnitude, that is the length of a vector, and find the angle that it makes. All right, so now the next key idea that we need to work through is to figure out how to add. So how do we add and subtract our vectors? Later in this course, we'll learn how to multiply vectors using what's called the cross product or the dot product. But for the first part of this course, we just need to focus on only adding them. And this is literally like a treasure map. You first walk along one vector, then you walk along another one. So the first thing that we'll look at for this is going to be called the graphical method. This one doesn't give you numbers, but it will show you roughly where you expect the vector to be. So this one, 100%, think about the treasure map. Whether or not it is a position vector, you want to still consider it just like a treasure map. So let's say that, for example, I have some vector A, which I'll draw in purple, and then I'm going to have some vector that I want to add it to, and I'm going to just draw a vector B straight down. So what would be A plus B? So in this case then, I can say A plus B would simply equal my vector A plus, I walk along A, I get to the end of A, and then I walk however B looks. So I walk along A and then I walk along B. And so my final vector then is just the vector that points from the start to the finish point, and that is my vector A plus B. So vector A plus B is what could you have done instead? Instead of walking around this crazy treasure map, you could have just started at the beginning, gone to the end, drawn a line from start to finish. That is your vector A plus B. So that's the graphical method. Now for subtracting vectors, still think about it as a treasure map. A minus B is simply equal to A plus negative B. So what this means then is that I would then take here my vector A, and then I'm going to add it to negative B, which is the same length as B, but in the opposite direction. So that would be my negative B vector. And then my total sum will point again from my start to the end. And so this vector here would then be A minus B, or A plus negative B. Another example of this is that if I wanted to show what negative A would look like, again, you would just draw the same vector that looks like A, but then the arrow's on the other side. So all it is it's the same length vector and it points in the opposite direction. So that allows us to get an understanding of how to add and subtract vectors visually, but very often we actually want to deal with the numbers. And so in that case then, what we have to do for our addition and subtraction is we would want to use what we'll call our unit vector notation, or say adding with components. So if I'm going to add these vectors, and again, it's the same as if I just walk along the treasure map. If I walk along A and then I walk along B and I end up where I needed to end up, well, I could walk all the X components first. So the X component of A plus the X component of B, and then I could walk all my Y components, walk along the Y component of A, and then walk along the Y component of B, and I'd end up at the same spot. And that's all it is when we add with components, but it allows us then to do it mathematically. So let's say that I have some vector C, which is going to be equal to the sum of A plus B. And let's define A as just having an X component AX, so AX I hat, plus a Y component AY J hat. And we'll define vector B as having an X component BX, and that's in the I hat direction because it's the X component, plus BY J hat. And as the semester goes on, if you're unfamiliar with the unit vector notation, you'll get more and more used to it because we just use it all the time. And so I encourage you to write as many vectors as you can that way yourself, just so that you get more and more used to it. So what we're going to do then is, if we think about conceptually what vectors are, well, if I want to get from, a walk along A and then walk along B, like I said, I could walk along all my X components first, And then that would get me to my final X location. So I could then say that C is simply going to be equal to AX plus BX. That'll be my final X component of vector C. So AX plus BX I hat. And then I'm going to walk along all of my Y components. And so then I would say plus AY plus BY J hat. And so I walk along my Y components and I end up at my final location. So AX plus BX would then be my X component of vector C, and AY plus BY would be my Y component of vector C. So this would then be the result, the unit vector notation for the sum of those vectors. Again, the magnitude of C would be equal to the square root of cx squared plus cy squared, and the angle tangent of theta would be equal to cy over cx. So I can still use those. Okay, so that concludes this video. What I'm going to do, because this is a more complicated video and many of these will have them, is that we are now going to have some quick checks. Some self-check questions. These are not turned in, but they're for you, now that you've viewed this video, to go ahead and pause the video, go ahead and work through these problems. They're very short. Make sure you understand it. And if you don't, you need to either rewatch the video or you can go back to some of the supplemental materials. So go ahead and pause your video. I'll wait a couple seconds in the video, and then I'm going to display the answers. So you can check them yourself and then move on. Okay, let me know if you have any questions.